Okay, section 8.4, the shortest path algorithm. A weighted graph is a graph in which values are assigned to the edges. Okay, the length of path in a weighted graph is the sum of the weight of edges in the path. Yes, this is a notation: weight of edges from I vertices to j vertex. In weighted graph, we often want to find the shortest path between two given vertices. Okay, let G be a connected and weighted graph. Then find the shortest path from a vertex A to vertex G. Okay, the well-known Dijkstra's algorithm involves assign labels to vertices. Okay, this you can find the more information of Dijkstra's algorithm on these web addresses. Okay, Dijkstra algorithm to find the shortest path between two vertices. And it fixed the unvisited vertex with the lowest distance and calculate the distance through it to each unvisited neighbor and update the neighbor's distance if smaller and mark visited when done with neighbors. So these are the algorithms that I mentioned. This can be written in this way. And let VV the labels, let L of V be the label of vertex V, and T is a set of vertices having temporary labels, and we'll circle vertices having permanent labels, and etc. Okay, each iteration of algorithm changes the status of one label from temporary to permanent. Okay, thus, we may terminate the algorithm when G receives a permanent label. And so, L of G gives length of shortest path from a vertex A to vertex G. Okay, and this is the Dijkstra's shortest path algorithm. I think we have taken a look on this. Okay, copy this. 리더라서 그렇구나. Okay. For example, this animation shows you how this algorithm works. Dijkstra's algorithm. 이게 이제 A서부터 시작해서 G까지 가는 문제라고 찾는 건데 여기서 이제 패스를 카운트 패스 여기 14이고 여기 7이죠. 그러니까 14보다 7이 가깝잖아. 그러니까 두 개를 비교해서 가까운 데를 두 번째로 잡는 거야. 여기서 갈 수 있는 것 중에서 또 이제 여기는 10이고 여기 15이잖아. 이쪽이 더 멀고 여기 더 가깝잖아. 그러면 그리고 또 이쪽에서 왔을 때 값하는 14하고 7하고 10이고 여기서 와서 여기 와서 이렇게 가는 거는 14하고 9하고 10이고 비교해 보면 또 여기서 일부러 갔다 2로 왔다가 이렇게 가는 알고리즘의 숫자. 그러니까 여기서부터 시작해서 여기로 가서 여기 가는 거 여기서부터 여기 가는 걸 이제 비교해 가지고 두 번째 어디로 가는 게 도움이 될지 자기 거 주위에서 고르게 이제 어차피 한 번씩 이렇게 가야 되는 것이니까. 그러니까 비교해서 이 중에 어떤 길로 가는 게 가장 효과적인지를 찾고 그 다음 그래서 찾은 거에다가 표시를 마크를 한다고 빨간색으로. 그럼 그 다음에 거기서도 똑같은 방법으로 어디로 가는 게 더 효과적인지를 세워서 다음 걸 마크를 해서 마크를 빨간색으로 한 개를 들면 이게 퍼머넌트 어드레스의 주인색이 되는 거고 그리고 그 다음에 이제 그게 마지막까지 해서 끝나면 그러면 알고리즘이 이제 완성이 되는 거지. 그걸 사람이 손으로 다 1 더하기 5 더하기 10 뭐 해보면 비교하는 게 별로 비효과적이고 그런 정도는 로봇한테 시킬 수 있으니까 이제 적당하게 알고리즘을 짜서 제공해 주면 제가 알아서 찾으면서 여기서부터 여기까지 가는 가장 짧은 길을 찾아주겠죠. 그게 디지털 알고리즘이에요. 그 알고리즘을 보여주는 애니메이션이 이거. Okay? Understand? Okay, this animation shows the Dijkstra's algorithm in move. Okay, so it starts from the vertex A, and it is going to end it at vertex 5, and he will find the best possible next move, and then he will he will change the color of the vertex to red, and then find the next permanent address for the vertex, and then until it ended to at vertex 5, like this. And this is the algorithm. Okay, so these steps were shown in here, and this is the pseudo code for Dijkstra's shortest path algorithm that you have seen in that animations. And also, I have made the code for those, and here, yeah, this goes show Hamilton. This goes this draw the digraphs, and if you add more, for example, Control C. If you want to add more edges from from A to C, then if you give a vertex from A to C, then you will see the graph which has another vertices. So you can draw any graphs that you want, and also, yeah, this gives you. You have to start. I defined the graph H, undirected graph. I draw the graph HD, and with those graph H and HD, I'm looking for the path of H and path of HD from here from 1 to 2. Here is the path from A to C. Okay, we can go from A to C directly, and we can go from A to C by start from A and next to B, then from B to C. There are two passes in HD graphs, and you can use this code for any others. And beacons number and similarity graphs, and here this is the hypercube at dimension 3. If you make it as the cube graph of dimension 5, then you will see a much more complicated one. If you want to see the dimension 5, the hypercube graph, and you can make it 100 or 200, whatever if you want. If you make 10, then how much? 2 to the 10th power. It's pretty big. It's going to be really big. You will see a lot of it. And as you see here, 어디 갔어? 너무 커져서 너무 커지니까 그렇죠. 이게 너무 커지니까 그림이 그려졌는데 어쨌든 여기에 그리려면 저게 좀 모자라니까 아홉 두께 클 거예요. 근데 중요한 건 뭐냐면 여기서 이게 버텍스들을 다 나열을 한 거 아니에요? 이제 그 다음에 넘버링을 해주고 하는 것들. You can draw all the graph. This is the complete graph of K5. If you want to have a complete graph of K3, then this is a simple one. If you want to have a complete graph of K7, then this is, you have a 7 vertices, and all vertices have 6 edges. And bipartite graph, this gives you a graph and bipartite graph. This is a graph example. This is a example of bipartite graph. And he's asking whether the given graph is bipartite or not, and this is not the ones. Is it bipartite? No, this is not a bipartite graph. You can ask it, you can check it. This is an example of complete bipartite graph, K42, and passes and cycles. You can find all the passes from 1 to 2, or you can find the pass from 1 to 6, then then give this is a path that you go from 1 to 6. There are two paths from 1 to 6, like this. And asking this graph is whether it's connected or not, and this says this graph is not. This graph is connected. But if you delete, for example, E1, like from 1 to 2, if you just delete this, then see what happens. Is this graph connected? This is 2, 3, 1, 2. 1, 2가 없으면은 1이 아이솔레이트가 돼 있는데, okay. Anyway, let's go. And yeah, this is subgraphs, and yeah, subgraph. This gives us subgraphs. And where is the Dijkstra's? And Königsberg-Burgess problems and Euler passes, and this gives you the degree of vertex 2. The G represents the graph, and this gives us the degree of vertex 2 in graph G. And as you see here, degree 2, the vertex 2 has 1, 2, 3, 4, 5 edges. So degree of this vertex is 5 from the definition. And yeah, this find the Eulerian circuit of this, and this is the Eulerian circuit of from this graph. And we studied the section 8.3 today, and this is Hamiltonian cycles. And here, from in this graph, yeah, this command gives us a Hamiltonian cycle in this here. This is a Hamiltonian cycle, traveling salesman problem. But if you go from here, from A, B, C, D, E, then this gives us the Hamiltonian cycle from this graph. If you draw the, and what else? Here, gray code and Hamiltonian cycles, and here, yeah, in here, a traveling salesman's problem from 4 cube, and this order gives you one Hamiltonian cycle in 4 cube. If you change it as 5, dimension 5, then you will have, yeah, you have 32 vertices, and in this case, yeah, we need to give a plot command to plot it because it's too complicated. So we need another command. But in this case, and this we have 8 vertices, and this is the one Hamiltonian cycle that we are looking for. And it's all that can be done with the modification of that code. And this is a nice tour that you just looked. And now we start the shortest path algorithm, and this is Dijkstra's shortest path algorithm. And yeah, you may here in this graph, this matrix is a representation of a graph here, and this gives us a shortest path, which is this from 0, 1 to 4 and 7, and this gives a shortest path from a graph which was given here, can be represented in a matrix representation of the graph like this. And so I may ask you to make a real code for this Dijkstra's shortest path algorithm, pseudo algorithms. You can easily find from other sources on the web to make it, so you can share it in iCampus. And yeah, these are the things yeah, we will cover, so I will continue it. But now I showed all the rest. For here, yeah, in section 8.5, yeah, we will learn the representation of graph, matrix representation of graph. For a given graph, adjacency matrix is defined in this way. And from if you have a edge from A to B, then A and B, this 1, 2 entry has 1. If we have AC, E here, then AE has 1 here, but we have only 2 edges, so in the first row you only have 2 ones, but all others are zeros. For DE, and from DE we have a 1 vertex, and from E to D there's another edge, so it has 2. Another 1 here, so we have a 2, something like that. So this matrix is defined as an adjacency matrix. And next, if we delete this, if you make a simple graph, then this can be simplified here without a roof. Then adjacent matrix can be drawn and can be found from the given graph. Graph can be shown in here. Its corresponding adjacency matrix can be found from the graph. You can easily define adjacency matrix. Then this matrix properties tell us the information of the graph, like this. The power gives us the length of the passes to reach, and it gives us the list of all the passes. There are 4 different passes from 2 to 4, like this. And the last part of this this section is incidence matrix. Here if we have a edge from V1 to the E1 connect from V1 and V4, then it has 1 and 4 has the 1 entries, and E3 has V and 2 vertices, then E3 has V1 and V2, and it has 2 non-zero entries in here, something like that. I will explain more detail. And anyway, from here, with this definition, we can find the instance matrix from a given graph without any difficulties. And also for the isomorphism, we can easily check whether the given 2 graphs are isomorphic or not. If we change it, then it will tell us it is not an isomorphics. Okay, that's the another way, one easy way to check whether the given graphs are isomorphic or not. And next, the last part is a planar graph, and we can check whether the given graph is planar or not. This is not a planar graph, and we can check the Euler's formula easily, whether it is true or not. And Grotowski's theorems and Euler's formula for a graph. I think that's the end of it. Anyway, you can check this code to have the visual understanding of the concept that we are learning in here. Anyway, Dijkstra's algorithms has been shown in this animations, and that algorithm was introduced, and you can find the real code of this pseudocode on Dijkstra's algorithms. Anyway, here in this example, the Dijkstra algorithm tells that start from A, then you check the distance between the nearest edges and counting it to find for example, you start from here. Then next, you have to choose one of B or D, and you compare. It is 1 and 2, so you choose the D as the second one, and then you compare the other vertices near, and compare those the length of the edges, the path, and then decide to the next vertex B, and then choose, compare to the older list, and choose the C, A, C, B, A, D, B, C, and mark it as red. Here is a black. Here is a blue, and then choose C, and then choose E, and then choose H. So what you found is here, from A to H, the shortest distance is A, B, E, H. That's the path, and distance is 2, 2, 1 is the shortest, like this. This is the way. You count all the best possibles and then compare the to discard the earlier inspections. So first you did choose it, but later when you find the ones, the next one, you decide the other one is better, then you choose B instead of D, and then you choose this, then counting it, and choose E to counting it, compare it, and discard it. And so that's the Dijkstra algorithm. That's what is written in here, and that's the explanation that choose the next vertex. And temporarily choose, and then compare, and when it's really done, it makes a permanent point and mark it as a red, and then find the shortest path to the end. Anyway, this example, show an algorithm 4.1, find the shortest path from A to G in the graph, figure 4.1, and figure 4.2 shows the result of executing lines 2 to 5. And this is the explanation here. 4 to 5 here. Actually, that's what I showed. That's what I showed in this. And that this is the explanation, and this is the same graph that you see from A to G. Find the path of 5. Next, Dijkstra's shortest path algorithm correctly find the length of shortest path from A to G. This is a proof, theorem and proof. The algorithm that we introduced and that you saw in here, and it is really work correctly to find the shortest length, and it's been proved. So now you can use this algorithm to find the shortest distance. Okay, and this figure shows how the algorithm works. Next, find the shortest path from A to G and its length for the graph of figure 8.4.7. Here, you start from here and you choose A first, then you choose the D, and then you choose B, compare those two, and you discard D, and you choose D, B, and then E and G. Here, in this case, you compare. So from A to G, the A to D to E to G, that is the shortest path compared to this or this. So this Dijkstra's algorithm tells us at the end, and this is the conclusion of it. Anyway, this algorithm have to count all the possible cases, so it takes time. So it is not with the big O notations. It takes this much of computational time. Big O, a big theta of n square in the worst case. So this is a kind of costly algorithm to find it. The last theorem shows the running time by using big O notations. It tells us theta of n square time is needed for this Dijkstra's algorithm. This is the analysis. And this is the problem that you're supposed to solve, or just you solve some easy problems that I gave you. That's your choice. Next, representations of graph. Our first method of representing a graph used the adjacency symmetrics. Here, the definition of adjacency matrix. From a graph, we can obtain a matrix. The correspondence is like this. The entry in a matrix from row I to J is if if I is not equal to j, the number of edges incidence on I and j. If I is not equal to if I is equal to j, then entry is twice the number of the loops incident on I. So here we label the rows and columns of a matrix with the ordered vertices like this. Here A to B, we have A to B is 1, but then A to C, there's no edge from A to C, so AC is 0. A to D, no, so 0. A to E, there's one edge, so it has 1 here. B to E, and B to E is 1. B to C is 1. And B to A, there is an edge, and all others are zeros. And for C, we have B, E, and C. So B, E, and C, we have non-zero entries here, but all the others are 0. For D, there are edges from to E, and from E to D, there are 2. So we have D to E. That's the only non-zero entries here, and all others are zeros. So do you understand how to make an adjacency matrix? From this graph, we can find, we can develop, we can construct a corresponding adjacency matrix with these rules. And the code that I made works for that. The reason that main diagonal entry, some entries has 2, that's the case then when you have this the loops, and but if we delete those loops, then the main diagonal entries should be all zeros like this. Anyway, the adjacency matrix is symmetric about the main diagonal, and information accepted on the main diagonal entries appears twice. Here, this is a simple graph. Then from here, the adjacency matrix can be defined in this way. From A has 2 edges. So in the first row, we have only 2 non-zeros, which is 2 B and D. For C, we have 3 edges, 2 B, D, E. So for C, B, D, E, only 3 has 1s, and other 2 entries are zeros. So like this. So I think you can find the adjacency matrix. 자, 윤소정. 자, 여기서 이 그래프를 보고 이 대응하는 adjacency matrix 만들 수 있겠어요? 별로 어렵지 않죠? 그러니까 여기서 보면은 뭐 B다 그러면 B에 3개 엣지가 있잖아요. 그럼 B에 대응하는 이 라인에는 3개의 논제로가 있을 거라는 거고, 위치가 어딘가 보면 A에, 또 C에, E에, A, C, E에 있는 있으면 되는 거죠. 그렇죠? 나머지는 그런 식으로 한 줄 한 줄씩 채우면 그러면 금방 그래프가 만들어지죠. 중요한 건 뭐냐면 이 그래프를 분석하려면 다 손으로 그려보고 확인해야겠죠. 근데 여러분은 매트릭스를 다루는 걸 고등학교 때도 조금씩 배웠죠. 그럼 이 매트릭스의 성질을 이용해서 여기서 복잡하게 해야 되는 걸 쉽게 구할 수 있습니다. 예를 들어서 여기서부터 A에서부터 E까지 가는 버텍스가 패스가 존재하느냐 아니냐는 것은 이거를 제곱해주고 세제곱해주면서 나중에 A 번째 로, B 번째 컬럼이 논제로가 되면 패스가 존재한다는 소리고, 여러 번, 5번, 6번 곱해줘도 계속 0이면 그런 패스가 존재하지 않는다는 소리. 무슨 말인지 이해해요? 그런 식으로 matrix knowledge can be used to understand the property of the graph. So, if A is the adjacency matrix of a simple graph G, then we can think of the power of matrices and discount the number or paths of various lengths. For example, vertices counted in this way, and consider the entry for row A and column C in A square. A and C. Okay, here we have 2. the number 2 obtained by multiplying pairwise entries in row A and then like this. We have 2 here. Okay, what this means is, this happens if there is a vertex V whose entry is in row A is 1. So from A to V, and if there is a vertex V whose entry in column C is 1, VC. So from A to V, V to C. So we can reach, we start from A to end it at C with 2 edges. So length is 2. AVC, which is length 2. So such edges from a path AVC of length 2 from A to C, and each path increase the sum by 1. So the sum is 2 because there are 2 paths, ABC and ADC of length 2 from A to C. So these numbers give us the length of paths from A to C. Okay? 그러니까 이 그래프 행렬의 파워가 여러분들이 어디서부터 어디까지 가는 패스, 즉 C에서 C로 가는 또는 D에서 E로 가는 패스는 존재하고 그 랭스는 1이라는 소리고, 뭐 E에서 C로 가는 랭스가 존재하고, 뭐 이런 걸 이 그래프만 보고선도 바로 이해할 수 있다는 소리. 행렬만 보고선도 이해할 수 있다는 소리예요. In general, the number of paths of length 2 from A to C, and that's the degree of C here. In general, those ideas can be expanded to the n by n matrix, and here, like this. If you suppose we have this graph, then this adjacency matrix can be written in this way. Then A square can be found in this way. This 2 means that there's a number of ways to get from A from B to D in 2 steps. And what else? The matrix power of adjacent matrix. That's what we did. Yeah, this is the explanation. If we find the adjacent matrix from a given graph, then the matrix power of that matrix give us the many informations, including the distance of passes from one vertex to the other. Next, if A is an adjacent matrix of a simple graph, then ijth entry of AN is equal to the number of paths of length n from vertex I to vertex C. This is what I said that the other example shows. And it can be shown by the mass induction. And this is example, also another example. A square, A force here. For example, if we have a 6 here in A force from D to E, what that means is the entry from row D and E is 6, which means there is 6 passes of length 4 from D to E. Like the force power, if we have a 6 here, then we have a 6 passes of length 4 from D to E. This is some information that you can draw from the adjacency matrix. And these are 6 passes from D to E that you can find the graph that gave us this adjacency matrix. Next, incidence matrix. To obtain the incidence matrix, we label the rows with the vertices and columns with the edges. The entry for row V and column E is 1 if E is incidence to V and 0 otherwise. Thus, the incidence matrix for the graph, the following graph, it can be written in this way. Here, if E is incident to V, the E1 is incident to V1, so it is 1. E1, V1. E1, E3 is incidence. Okay, so V3, E1 and V3, E3, V1, E3, this is 1. For example, V3 with E6 is incident to V3 and V5. So V3 has E6 has what? V3 and 5 has ones and all others 0. Got it? 이게 무슨 말인지 알겠죠? 그러니까 엣지들로 보면 엣지가 하나, 둘, 셋, 다섯 개 있잖아요. 엣지 이거는 이거 두 개가 포지션이 있고 나머지가요. E2에 대해서는 이거 V3가 있고 0. 그다음에 E3의 경우에는 첫 번째, 두 번째, 첫 번째, 두 번째가 이렇게 나오죠. E4는 4하고 2, 4. 2하고 4만 있고, 5는 2하고 5. 2하고 5. V6는 3하고 5. V6는 3하고 2, 7은 그냥 혼자 V2에만 연결되어 있잖아요. V2만 무슨 말인지 알겠죠? 그러니까 엣지별로 엣지를 컬럼으로 하는 그 보텍스에 대한 그런 제로 원을 구분할 수 있죠. If we and also this incidence matrix give also very interesting information of the graph as well. So, but and we gave two problems to be solved about the adjacency matrix. 여기서 보듯이 adjacency matrix is more important and more interesting. So I only ask you to play with these two problems on adjacency matrix because that's more important. Next, isomorphism of graphs. Isomorphism of graph. Yeah, we have two graphs like this. Okay, but what we want to tell is basically these two graphs are same, structurally same. We call these two graphs are isomorphic. Then when we call two graphs are isomorphic. 김구는 지금 저기 궁금한 거 있으면 계속 질문을 10개쯤 하고 가도록 하세요. 가기 전까지. 오케이? 가만히 있지 말고 계속 질문하고 가세요. 오케이. Two graphs are isomorphic. 그리고 또 학생들이 자네 질문에 답을 준 게 있지? 그 답에 대해서 이해했으면 고맙다고 얘기를 하고 이해가 안 됐으면 이해 안 된 걸 또 물어보고 계속해서 자네가 이해될 때까지. Okay? Okay, two graphs are isomorphic. This is a definition. Two graphs are isomorphic if there is a one-to-one onto function f from the vertices of G1 to vertices of G2 and one-to-one and onto function G from the edges of G1 to edges of G2 so that the edges is incidence on V and W in G1 if and only if the edges of G of E is incidence on F of V and F of W in G2. 무슨 말인지 이해되겠어요? Do you understand? For these two graphs, for example, if we define a function f and g, one-to-one and on-to function, that send little a to capital A, little b to capital B, little c to capital C, little d to, and but edges x1 to y1, x2 to y2, and x3 to y3, dot, dot, dot. As you see here, this f and g is a one-to-one and on-to function, okay, bijective function, and the incidence vertices of each edges are exactly matches with the original one, like this. For example, 여기서 A2가 연결돼 있죠. 그럼 여기서는 A하고 그러면 여기서 A하고 E가 뭐 Y1으로 연결돼 있지. 그러면 여기서는 A하고 E가 여기 X1으로 연결돼 있죠. Y1으로 연결된 게 X1으로 연결돼 있고 여기서 B하고 C가 X3로 연결돼 있죠. 그럼 여기서 캐피털 B하고 캐피털 C가 Y3로 연결돼 있죠. 그러니까 이게 지금 캐피털이 소문자가 대문자로 바뀐 거하고 X가 Y로 바뀐 거 말고는 구조가 다 똑같이 돼 있는 거죠. 배치만 바뀐 거지. Okay? So these two functions are one-to-one and on-to, and the incidence vertices of each edges are preserving the positions and orders. So by the definition, these two graphs are isomorphic. These isomorphic relations, if we define an R as the relationships like this and isomorphism, then these isomorphic relations form an equivalence relations. Okay? And each equivalence class consists of set of mutually isomorphic graphs. 그럼 이게 무슨 얘기를 하는 거냐면 그 그래프들이 이렇게 있으면 아이소모픽한 그래프들로 다 클래시파이 할 수 있다는 소리죠. 콩그런스, 동시류를 만들 수 있다는 소리죠. 이퀴버런스 릴레이션은. 그래프를 전체를 다 분석할 필요가 없이 이런 성질을 가진 거, 이런 성질을 가진 걸로 분류한 몇 개만 하면 그런 모든 그래프를 다 같이 연구할 수가 있죠. 그러면 콩그런스로 분류해, 그러니까 이퀴버런스 릴레이스가 있으면 콩그런스 클래스로 분류를 할 수가 있고, 그러면 여러분 있잖아요. 알고리즘 하나 갖고 모든 케이스를 다 분석할 수가 있게 되는 거죠. Okay, the graph 6G and G2 isomorphic if and only if for some ordering of their vertices, their adjacency matrix are equal. 그러니까 여기서 얘기하는 거는 이게 이 아이소모픽이 굉장히 중요한 개념이야. 굉장히 단순하신 것입니다. 거기에 이 그래프 아이소모픽화되는 것을 이 adjacency matrix를 이용해서 바로 if and only if로 찾을 수 있다는 소리죠. 그러니까 those matrix, adjacency matrix can be used to decide whether to given graphs isomorphic. 그러니까 그래프 두 개를 보고서는 이거 아이소모픽 하는 건 아까 볼 때 이 그래프 두 개 보고서는 함수를 찾으니까 이해가 되지, 이거 보고 아이소모픽은 잘 안 보여지죠. 근데 요거의 adjacency matrix 한번 구해볼까? 그러면 adjacency matrix가 다 this is adjacency matrix of the graph, the first graph, and this is adjacency matrix of the second graph. 그러니까 그 adjacency matrix 그래프의 정의에 의해서 그래프를 구하는 그 adjacency한 그런 그 성질들이 그래프에 따라서 그래프를 그려지고, 그러면 이 두 그래프가 같다는 소리가 바로 그 정의에서 그 버텍스들이 1대1 대응이 되고, 그 다음에 그 저기 엣지들이 서로 연결하는 엣지가 그 위치에 있는 그 엣지라는 것이 확인되는 거죠. 그러니까 if 그 adjacency matrix가 같으면 그냥 그 투 그래프는 아이소모픽한 그래프라고 얘기할 수 있는 것이죠. 훨씬 쉽죠, 파악하기가. 이 함수를 찾는 것보다 finding these two one-to-one and onto functions are much complicated to find two adjacency matrices. 그리고 아까 내가 코드를 보여줬죠. 그래프만 주면 adjacency matrix가 그냥 찾는 코드를 주어서 바로 adjacency matrix 찾을 수 있었죠. 그래서 아무리 복잡하더라도 그 두 개가 같으냐 아니냐 비교하는 명령 하나만 주면 그 둘이 아이소모픽이 아니냐 코드를 바로 짤 수 있지. 그렇죠? Okay. So since you know how to find the adjacency matrix of a given graph, so you can easily check whether the two given graphs are isomorphic or not by the above theorem. Okay, and in order to show two simple graphs are not isomorphic, all you have to do is just find the property of G1 and that G2 does not have, that G2 would have if G1 and G2 are isomorphic. 무슨 말이냐면 두 그래프가 아이소모픽인 거를 아이소모픽이 이제 보이는 건 그렇게 보이면 되는 거잖아요. 그래프를 그려서. 근데 아이소모픽이 아닌 걸 보이려고 그러면 이게 아이소모픽이면 그 두 개의 그래프가 갖는 성질이 같이 갖는 성질이 있을 텐데 하나는 그 성질을 가지고 있고 하나는 그 성질을 안 가지고 있다 그러면 둘은 아이소모픽일 수가 없는 거죠. That's the another easy way to check whether the given two graphs are isomorphic or not. 그렇잖아? Okay, so that property is called invariant. So property P is invariant if whenever G and G2 are isomorphic graphs, then both has the same properties. 그러니까 이 그래프 아이소모피즘에 대해서 이제 프로퍼티가 인베리언트하다는 것은 아이소모피즘이죠. 두 그래프가 아이소모픽이면은 여기서 가는 성질은 언제나 여기서 같은 성질. 그럼 인베리언트 성질이 몇 개인지만 알면 나중에 분석할 때 이게 가지고 있는 성질이 여기 없으면은 그러면 아이소모픽하지 않다고 얘기할 수 있다는 소리예요. 예를 들어서 those are if G1, G2 are isomorphic, then there is a one-to-one and onto function from the edges of G2, edges of G1 to G2. 그러니까 엣지에 대한 원투원 앤 온투 펑션이 존재한다는 게 이제 아이소모픽에서 아이소모피즘 그래프가 갖는 성질 중에 하나, 인베리언트한 성질이에요. So, if Gn and G2 isomorphic, then G1 and G2 have the same number of edges and the same number of vertices. 그러니까 엣지의 개수도 같아야 되고 버티스의 개수도 더 보존해야 되는 거야. 아이소모픽 하려면 원투원 앤 원투 펑션이 존재해야 되니까. 그래서 in this case we have 1, 2, 3, 4, 5, 6 and 7 here. 하나 둘 셋 넷 다 일곱 하나 둘 셋 넷 다 여섯. Here we have 1, 2, 3, 5 vertices and 5 vertices, but it has 1, 2, 3, 4, 5, 6, 7 edges, but this one has only 6 edges. So these two graphs cannot be isomorphic. If they are isomorphic, the number of vertices and number of edges should be same, but number of edges are different, so they are not isomorphic. And in this case also, it has 2 edges, but it has 3 edges, so they cannot be isomorphic. Okay, so if k is a positive integer, then it has a vertex of degree k. That is invariant property. And also here, non-isomorphic. Here, we can tell these two graphs are non-isomorphic. Why? If you see here, every vertex is here. It has what? Every vertex has a degree what? 3, 3, 3. 1, 2, 3, 1, 2, 3, 4. Here, it has a degree. It has a vertex which has degree 4 here. But in here, every vertex has no degree of 4. No, this one has 4. What is this? Okay. Here, G1 has vertex of degree 3, but G2 has no vertex of degree 3 here. For example, here, it has a vertex which has degree 3 here. But in here, it has degree 2. This vertex has degree 4. Degree has 4, 4, 4, and 2. So, there is no edge, no vertex which has degree 3 in here. So this cannot be isomorphic because the number of edges and number of vertices is same, and each of 그러니까 이 어드제이션스 매트릭스가 같으려면은 그 매트릭스 안에는 논제로의 개수도 똑같아야 되죠. 그러니까 하나의 버텍스가 갖는 그 디그리, 그 엣지의 숫자가 똑같아야 된다는 소리죠. 근데 이게 여기는 3개짜리가 있는데 여기는 3개짜리가 없잖아요. 그러니까 한 로우가 하나는 제로가 3개가 논제로가 3개가 있고 하나는 논제로가 3개인 로우가 없다는 소리지. 그러면 두 행렬이 같을 수가 없지. 그러면 당연히 에디제이션 매트릭스가 다르지. 에디제이션 매트릭스가 다르면 아이소모픽일 수가 없는 거죠. Okay. So many things can be found by just evaluating such properties. Here, in this example, checking an invariant property, cycle of length 3. These two graphs are non-isomorphic. Why? In this case, G2 has a simple cycle of length 3, but G1 has no simple cycle of length 3. Here, 여기서는 그 length 3인 게 the simple cycle. Here, G2 has here. 그러니까 1에서 예를 들어 4로 갔다 8로 갔다가 1으로 오는 그 랭스가 3인 사이클이 존재하죠. 마찬가지로 여기서 또 하나 1에서 2로 갔다 5로 했다 다시 1로 오는 사이클. 랭스가 3인 사이클들이 여기 여러 개가 있죠. 근데 여기서 봐봐. 이 A에서 D로 갔어. D로 해서 A로 올리면은 B로 가는 방법이 B로 가려면 F를 거쳐서 가야 되니까 4개가 되고 C를 갔다 와도 3 가다가 G를 거쳐서 오거나 E를 거쳐서 와야 되고 그렇죠? There is no cycle of length 3 in here. So 그러니까 사이클도 아이소모픽하면 보존해야 되는데 그것도 이제 똑같은 행렬이면 파워했을 때도 그 똑같이 그게 저기 행렬이 같은 행렬이 나타나야 되잖아. 그러니까 파워했을 때 그 사이클의 랭스 그 첫 번째 논제로 엔티티가 나타나는 그런 거. 세 번째 파워했을 때 행렬도 똑같아야 될 거 아니야. 근데 여기는 1이 있고 여기는 0이 여기 1이고 여기는 0이면은 두 행렬이 다르다는 소리는 행렬 A가 다르다는 소리지. 그렇죠? adjacency가 다르다는 소리죠. 그러면 그 두 그래프 adjacency가 다르면 그래프가 아이소모픽이 아니라는 소리죠. 하는 식으로 행렬의 파워만 가지고도 여러분들이 아이소모픽 아닌 걸 찾아낼 수 있는 방법이 굉장히 많이 있다는 거예요. So from those invariant property of the isomorphic graphs, you can easily find it here. 여기서 보면 this G1 has no cycle of length 3, but this one has. There are two problems that you're supposed to solve. 자, 8장 담당한 조가 누구예요? 8장. 뭐 어렵지 않지 다. 문제들 이미 다 했지? 아직도 안 했어? 이세영 양 다 풀지 않았어? 하고 있어요? 다 간단한 문제들이니까 그러니까 그냥 바로 하세요. Next, planar graph. planar, section 8.7. planar graph. It's also called as a plane graphs. Okay, a graph is planar if it can be drawn in the plane without its edge crossing. So planar just means we can draw it without intersecting lines. 무슨 말인지 알겠어요? 이 그래프를 그릴 때는 서로 다 이렇게 그 여기서 여기 연결할 때 서로 다른 엣지를 넘어가지 않고 그릴 수 있었지. 근데 어떤 그래프들은 이거에서 이걸 그리려 그러면 이게 그래프 케이스 이거를 이쪽으로 돌리고 이 선을 꺼내서 이쪽으로 돌리고 이쪽으로 꺼내서 돌리고 하더라도 어느 순간에는 여기서부터 연결하려면 저기 하이웨이를 건너가지 않고는 즉 오버브릿지를 만들지 않고는 연결할 수 없는 그런 그래프들이 있죠. 그거를 플래너 그래프하고 아닌 걸 구분하는 거예요. 무슨 말인지 알겠죠? 하이웨이를 이렇게 놓을 때 그럴 때 이 오버브릿지가 필요하냐 안 필요하냐 이제 그런 의미로 이해하면 돼요. 플래너 그래프. 그러니까 펜 가지고 그냥 엣지를 서로 끊어가지 않고 이렇게 돌아서 연결시킬 수 있냐 없냐 하는 그런 거. Okay. So if A is connected, the planar graph is drawn in the plane, and plane is divided into faces. 이렇게 플래너 그래프에서 이렇게 잘라지면 그러면 구분할 수가 있죠. 요런 엣지들의 안과 밖을 구분할 수 있지. 서로 이게 막 중간에 끊어지고 그러면 그렇게 구분을 할 수가 없고. Okay. So 이게 if you see here, then we have edge, we have vertices and edges, and also we can have faces here and there. Then there is a relationship between those vertex and edges and faces, like this. We will study it. This is called the Euler's equation. It satisfies these properties always. Anyway, case 3.3 is not planar. Complete graph. Case 3.3 is not planar because it does not satisfy that Euler's equation. That's why, this is not planar. But we can think the series reduction, this definition, series reduction, which means delete some vertex to find another graph from the given one. For example, if we have this graph, then we can, if we delete this vertex and this vertex, and then just connect it, then we can simplify this graph to this one. 그러니까 불필요하게 중간에 있는 이런 버텍스는 없는 걸로 치는 식으로 버텍스를 빼버리면 그럼 이런 심플 그래프가 만들어질 수 있죠. 그래서 버텍스를 딜리트하는 그렇게 해서 새로운 그래프를 만들어내는 것을 이 버텍스 시리즈 리덕션이라고 그래요. 시리즈를. Okay. With this series reduction, we can do this. In graph G of figure 7.4, the edges V1, V to V1, and V to V2 are in a series. This was there, but in graph G prime, if we delete this V vertex, then we can have another graph like this. Then we call this graph G prime is obtained from this graph G by series reduction because we deleted this part. Okay. Series reduction. Why this is important? Definition homeomorphic. G1 and G2 is isomorphic after some series reduction. After some series reduction, if two graphs are isomorphic, then we call those two graphs is homeomorphic, not isomorphic, but homeomorphic. Okay, like this. This graph, we delete this and we delete this. Then we can have, and okay, we can delete this. Then this can be reduced to this, and this graph can be reduced to this one. Okay? Then what we can tell is if we with the series reduction, this can be made this and this can be this. What we delete, this means these two graphs are homeomorphic. They are not isomorphic because the number of vertices are different, but these are homeomorphic. 그러면 우리가 이런 비슷비슷한 그래프들을 다 다르다고 해서 그냥 연구를 포기하는 게 아니라 이것으로 이런 것들을 연구해서 이것에 대한 성질을 찾는 걸 갖고 다 이거에 대한 답을 줄 수 있죠. 이런 것들은 이 그래프들은 이거랑 별 차이가 없죠. 큰 기란에 대한 정류소가 하나 더 있는 거야. 거기 들었다가 안 들어가는 건 없잖아. 그게 전체 길이의 숄티스트 패스를 찾거나 숄티스트를 찾거나 하는데 별로 영향을 전혀 미치지 않죠. 그렇지 않아? 거기는 어차피 지나가면서 그냥 그런 건 연구에 전혀 문제가 되지 않아요. 어차피 지나가야 될 길이니까. 무슨 말인지 알죠? 그러니까 트래블링 세일즈맨 프로그램 같은 걸 할 때 뭐 저런 거는 그냥 이 문제만 연구하면 다 구해지는 문제이기 때문에 별로 호메오모픽한 그래프만 연구해도 답은 다 줄 수가 있는 거죠. Okay. So this homeomorphism is also important and interesting. Define a relation R on a set of graphified rules, this, the homeomorphy, then it is also equivalence relation. So each equivalence relation consists of a set of mutually homeomorphic graphs. So this equivalence relation gives us a congruence class. So we can simplify whole such graphs in certain categories to be analyzed. The Grotowski's theorem, which can be found in here, is explained in detail here. And in graph theory, Grotowski's theorem is a mathematical forbidden graph characterization of planar graph. This is one of the most important property on planar graph. Okay, what it is this. A graph G is planar if and only if G does not contain a subgraph homeomorphic to K5 or K33. So if we want to know whether a given graph is planar or not, but by checking it is kind of is boring. We have to check all those the relation. We have to draw those. So the Grotowski found a theorem if and only if he found the if and only if condition. If G does not contain a subgraph homeomorphic to K5 or K33, then it is planar. This is simple. 그러니까 플래너 그래프인지 아니면 플래너 그래프이면은 그다음부터 할 수 있는 게 굉장히 많아지는데 플래너인지 아닌지 확인하는 게 굉장히 힘든데 그 안에 좀 단순화시켜서 딜리트 없애고 해서 이런 K3나 K5가 있는 점을 확인하면 이런 게 하나만 있으면 그러면 그거는 플래너가 될 수가 없다. 이거 될 수가 없거든. 아까 하는 걸 봤지. 이런 게 하나만 있으면 무조건 여기에 더 버스에서 4개 더 있어도 어차피 플래너그래프 안 되는 거죠. 그러니까 그거 말고는 없다. 그 안에 저것만 없으면 다 플래너그래프라는 소리야. 그렇죠? 그러니까 굉장히 쉬운 문제로 바꿔준 거죠. So Grotowski had made a great contributions. So for example, here, so okay, so this is the Grotowski theory. Here, for example, the graph G in figure 7.6 is not planar because from here we can delete. We can delete AB. We can delete AB edges. We can delete this AB edges and FE edges. Then this graph can be simplified in this way. Then we can delete this H vertex. Okay, and then how do we delete with the series reduction? We take a series reduction on G and H. Then what do we have? We have K33, isn't it? 자, 이 그래프에서 지금 여기서 잘 안 보이지나? 자, 여기서 요 엣지 두 개를 요걸 떼어냈어. 떼어내니까 이런 모양이 됐죠. 그 다음 시리즈 리덕션은 요걸 없애버리면 여기서 이렇게 바로 연결되죠. 그러면 여기서 엣지가 다 세 개 다 세 개. 그러니까 버틱스가 세 개씩인데 다 세 개씩 갔다니까 모두가 연결되니까 바이파타이트 그래프가 된 거죠. 그럼 K3가 되는 것이죠. 그러니까 이게 서브 그래프가 되는, 일단 이거는 이거의 서브 그래프지. 서브 그래프인데 요걸 시리즈 리덕션을 하면은 이게 K3하고 호메오모픽하죠. 그러니까 this graph에서 서브 그래프 which is homeomorphic to K3. So this graph cannot be a planar graph. That's the proof. Okay? This is the explanation that I gave you. This is a complete graph, bitype graph K33. So, since this has a homeomorphic graph, subgraph to K33 in it, so this graph cannot be planar. Okay, next, last part is Euler's formula for graph. I think you have learned this. 그러니까 이 Euler's formula for graph에 대해서 배운 적이 있죠? 자, 윤소 정량. 이거 본 적 있죠? 언제 봤어? 처음 보게 왔어요. 중학교 때? 이거 보통 어렸을 때부터 많이 보는 거예요. 하다못해 책종이 그림 그릴 때부터도 저거 숫자 세고 하면서 비교해 보니까. 자, as you see here, for this graph, always it satisfies this Euler's formula. This graph also. So the Euler's formula for graph, you can listen it. There are lots of explanations.
In my video on the circle division problem, I referenced Euler's characteristic formula, and here I would like to share a particularly nice proof of this fact. It's very different from the inductive proof typically given, but I'm not trying to argue that this is somehow better or easier to understand than other proofs. Instead, I chose this topic to illustrate one example of the incredible notion of duality and how it can produce wonderfully elegant math. First, let's go over what the theorem states. If you draw some dots and some lines between them, that is, a graph, and if none of these lines intersect, which is to say you have a planar graph, and if your drawing is connected, then Euler's formula tells us that the number of dots minus the number of lines plus the number of regions these lines cut the plane into, including that outer region, will always be 2. Because Euler was originally talking about 3D polyhedra when he found this formula, which was only later reframed in terms of planar graphs, instead of saying dots, we say vertices. Instead of saying lines, we say edges. And instead of saying regions, we say faces. Hence, we write Euler's discovery as V minus E plus F equals 2. Before describing the proof, I need to go through 3 pieces of graph theory terminology. Cycles, spanning trees, and dual...
Here. Okay, so you can, you have seen this and you can easily find how it works. But important thing is this: the number of faces is same as the number of edges minus number of vertices plus 2. This always satisfies if it is a planar graph, connected planar graph. This is important. With this theorem, we can also draw the other related theorem like this. If it is a planar graph and set of faces is f, then the addition of degree of each vertices in each faces, the sum of it is equal to same of double of the number of edges. Okay? Because every edges is counted twice. 이 무슨 말인지 이해되겠어요? 되니까 다 합쳐놓고 보면은 엣지들의 숫자의 2배만큼이 바로 버틱스의 그 디그리들을 합친 거하고 같아진다 그런 소리예요. Because this edge is counted in this side and the other side as well. So always edges are counted twice. So this relation should be satisfied. I think that's the end of chapter 8. And these are the problems. You can solve these two problems in the chapter book, or just simply solve these 5 problems in which I gave you. I think that's the end of week 13. So we now only have left chapter 9, which is 3, which is much simpler than the earlier part. So after that, yeah, we will. So you every problem that you have, you will be completed by the end of next week. Then I will assign your duty to present the revision of your PBL report and your solutions before in 15th week. Then we will have the final exam on 16th. Okay? So we now only have 1 week to cover to finish up our semester. Then 1 week for presentation, which is your part of examination and also PBL report. I think that's the end of today's class. Any questions?